Okay, everyone, we're back for the part B of the question. So now is where we're going to relate the complex numbers to the cubic function, and in particular, at the end of the day, what we're going to do by the end of this, and at the start of part C, is we're going to actually prove Cardano's cubic formula in yet another way. The depressed version, obviously, because there's nothing in front of the x cubed here. So they say out of the blue, in this problem, consider the cubic equation x cubed minus 3px plus 2q equals 0, where p and q are real numbers. That's what this means over here. Assume you can then factorize it as x plus alpha plus beta times x plus omega 1 alpha, omega 1 being the complex root of unity, second complex root of unity here, x plus omega 1 alpha plus omega 2 beta times x plus omega 2 alpha plus I'm sorry, that should be an omega 1 beta. Omega 2 alpha times omega 1 beta. And unfortunately, you kind of just have to roll with it. But to give kind of a naive understanding of why this sort of works, and I might like link a text description of a more clear expert at this thing who I had a discussion with in the video here. But this basically comes from like Galois theory or field theory. Which is basically a subject that takes this algebraic structure called fields and turns things into groups. And then we do algebra with it so that we can solve it a lot easier. As far as I can tell, this thing here, oh sorry, I should mention what the alpha and beta first, my apologies. Alpha and beta are roots of the cubic. Now what omega 1 alpha plus omega 2 beta here is using some loose term from linear algebra. You're taking a linear combination of these roots. Therefore, you are finding what these roots to your cubic polynomial, x cubed minus 3p cubed plus 2q are, and then you're scaling them. You're scaling them, changing their length, dilating their length by the amount of these complex roots here. Omega 1, omega 2, omega naught. Now, unfortunately, I should say, it doesn't really change the length because the circle we're dealing with is a unit circle here in radius 1, but every time you multiply by these roots, omega naught, omega 1, omega 2, you are rotating your roots of the cubic function around this weird circle. And that somehow has to do with like Galois and field theory, which I'll leave it for this very nice commentator to go and explain this section. But yes, we just have to roll the punches with here. And now comes the first question. Unfortunately, the Revision Village made a typo here. They said identify sum of roots, and therefore conclude 2q equals alpha cubed plus beta cubed. My apologies, I'll write here again. Alpha beta, two possible roots of cubic. A depressed cubic in this case, depressed. Because it has no quadratic term, and you can check my own video of the deriving the depressed version of the cubic formula if you want to know more. So 2q equals alpha cubed plus beta cubed. The 2q corresponds to this thing here. However, the last term of a polynomial is not the sum of the roots. It is the product of the roots. So that was an unfortunate typo on that part. And now we're talking about sums and products of roots of polynomials. We're essentially going to be appealing to the Vieta formulas, essentially, or, oh yes, the French worked on them a lot, but also like the ancient Chinese worked them for many decades, millennia, a while ago. But I don't know the names of mathematicians, unfortunately, aside from Vieta. So anyhow, the product of roots, and I'm going to use pi notation here, the product of roots is defined by take -1 and you raise it to the degree of the polynomial, in this case 3. Let me check that I have that right here. There's a lot of careful bookkeeping I need to look at for this. Wait, sorry, my apologies. Minus 2q alpha beta squared, 2q alpha cubed, beta cubed. Oh, okay, there's this problem. Now we're going to use sum and product of roots. We're going to have to use all the parts that we did in like part A to help us as well. So this is going to be hell. This is going to be hell, unfortunately. So then product of roots, I remind you, and it's also in the formal booklet, you have -1. Yeah, let's define the roots. Let's define the roots. I'm sorry, I just realized I made this error. Alpha and beta, my apologies for that. Alpha and beta are not the cubic roots. Like this alpha and beta is one root. This omega-1 alpha plus omega-2 beta is a second root, and this omega-2 alpha plus omega-1 beta is another root. Let me check if they... No, they do not define what alpha and beta are. I don't know if they are complex numbers or real numbers, but unfortunately understanding that is for the tasks of Galois theorists, and that is beyond our pay grade at this moment. But I just want to correct that over there. So just to make it nice as I did over here, let root 1, I just have to do the negative of this stuff. Set this equal to 0 and then solve. So the root 1 equals minus alpha minus beta. Root 2 equals minus omega-1 alpha minus omega-2 beta. Root 3 equals minus omega-2 beta alpha minus omega-1 beta. Actually, yeah, instead of using that pi or that sum notation, let's just like multiply them and like add them together. Just so that we don't bore people off with the symbolic notation. So then this, which is these things multiplied together, is by Viet. By Viet, or the Chinese, -1 to the n, a naught over a n, where n is the degree of your polynomial, and a naught is the constant term, or the last term of your polynomial. Oh, and an is the leading coefficient of your polynomial. So the degree of this polynomial is 3, so we have -1 to the 3. A naught we take in our 2q. And then we divide by, there's nothing in front of the x cubed, so that's just 1. So we get a minus 2q. Okay, but now the real work comes from multiplying all this entire garbage next to each other. So I'm going to erase this now. Just last minute look before it goes bye-bye. So this equals minus 2q. Now we have to multiply all this junk together and then use the previous results that we found in our problem. Oh, I just realized I should have erased that. I wasted so much time. Apologies. Okay, let's see. Oh, why did I get rid of the... Oh, okay, yeah. So you're going to have negative signs when multiplying this, but there's free roots. So then again, you get like minus 1 to the free. Just because you like put the minus sign from them naturally. And then you get the same result, alpha plus beta, omega 1 alpha plus omega 2 beta times omega 2 alpha plus omega 1 beta. And then this just becomes pain. This just becomes pain. Endless, endless, miserable pain. Minus 2q here. Particularly, we multiply this expression with this expression here. So we get alpha. This negative 1 and this negative 2q will cancel here. So I should have the negative 1 right here first. So then this is negative alpha plus beta times omega 1, omega 2, alpha squared plus omega 1 squared plus omega 2 squared alpha beta plus omega 1, omega 2, beta squared. Yes, we're good. And now we use a key result, but from part A, this is the key skill that you have to use for like these IB papers all the time. So omega 1 squared plus omega 2 squared equals omega 1 plus omega 2. And thank goodness that we also proved in part D was equal to negative 1. So all that just becomes as negative 1. So then we get minus alpha beta. Don't forget also, we also concluded, so this was a whole part that we assumed, sorry, not assumed, that we proved. We also proved that omega 1, omega 2 is equal to 1 as well, because let's see, that's the final result, right? Omega 1, yep, is 1. So this just becomes 1. This becomes 1. This becomes 1. This gets annihilated. I'm sorry. It doesn't get annihilated. I was too trigger happy to go on the cancellation there. It becomes negative 1. So we just get negative alpha plus beta. Actually, I'm going to get rid of now. This negative 1 over here cancels with this negative 1. So you get 2q equals alpha plus beta. This is then times alpha squared minus alpha beta plus beta squared. Boom. And then we just go and multiply that out. So that's alpha cubed. You could use the box grid multiplication technique if you want to help make this grid look easier. You'll have 2 times 3, 6 terms, so your array there would be a 3 by 2 grid in that manner. And now we just have to go for the word alpha squared beta plus alpha beta squared plus beta alpha squared minus alpha beta squared plus beta cubed, and there's obviously some cancellation that happens here. Let's see. Let's do it in color coding just to make it easier. This gets deleted with this, and that gets deleted with that. So in the end, I think it's a Linkin Park song. So we get 2q equals alpha cubed plus beta cubed. Okay, so a lot of what we did earlier, like, helped do a lot of the grunt work for us, otherwise we would be going through hell right now. And then that's the part 1 of problem B solved, but then next, let's see. Another formula for the roots of, oh yes, okay, so there's the sum of the roots formula for a polynomial. There's the product of the roots for a polynomial, but then there's this accursed third formula from the Viet polynomial roots, and this is where it becomes hell. Okay, so let me erase this. I'll erase this in the meantime. I'll just mention in the meantime I found I never could get used to color code annotation for like annotating my books for like linear devices, for linear analysis essays, because if I mark up the wrong thing, it's impossible to erase. But like here, for like whiteboard stuff, I find it very, very useful. Very useful in this regard. Helps notice like what parts you're going to cancel or introduce like a random factor. You know, multiplying by 1 and adding by 0 and that stuff. Okay. Okay, just to make more room here. And just write the next result in case we're going to need to use it. 2q equals alpha cubed plus beta cubed, check. That is done. We might use this if need be. Okay, then we have this cursed formula that R1, R2, oh wait, I did it capitalized. We have it lowercase, but let me do it capitalized. R1, R2, they basically pair off each of the roots, multiply them with each other, their corresponding products, and then add them all together. Which sort of looks like, but it's not quite linear combination-y, or some of the sort. And they say that this equals to negative equals CA. Which really all that is in the most general case, excuse me, my throat. Yeah, this is where it helps to, if we write the general form of a cubic function, f of x equals ax cubed plus bx squared plus cx plus d. The CA they're referring to is you take the linear coefficient and then you divide it by the leading coefficient. In this example, so linear coefficient divided by the leading coefficient, which is a cubic in this case. In general though, this thing, which, oh dear God, I don't even want to write this out in like the summation big sigma and big pi notation form. This thing in general for any, let's call it linear combination of products or what have you, is equal to this here, which is, let's see, it's over the leading coefficient. So this is the leading coefficient. And I guess all I could say is this is the coefficient of n minus 2th term. So you look at the leading term of the polynomial you have, and then you move 2 places to the right, and then pick that term, whatever it is. So if you have like a quintic, which is a degree 5 polynomial, you get the degree 5 polynomial coefficient, put it at the bottom, move to the right, that's 5 minus 2, you get 3. You get the cubic term, find the coefficient and put it in there. But what is it in this context for this problem? Well, the C, because the quadratic term is gone for this depressed cubic, it's simply going to be minus 3p here. And the A is just 1 in front, so it's just minus 3p at the end of the day. So yeah. But yeah, lots of connecting stuff. We have trigonometry, we have complex numbers, we have roots of complex number, roots of polynomials, all in one go. It's a big mess. It's a big mess, I tell you. It's minus 3p over 1. And then you have to do the stupid thing. And now I kind of want to face slam myself on the whiteboard a bit. I could do it for you if you want. Not hard enough, but like, yeah. My whiteboard is a bit fragile. Okay. Yeah, you just have to. You just have to do it. And like, if you follow my work, then kudos to you. This I would expect like one can easily make so many errors on, and it's fine if we just pray that the IB examiners are charitable to you and give you partial points for this. Although this problem is already ridiculously long, so it is not realistic of an actual IB paper-free problem. It's just good for practicing all the concepts. So this thing here equals, I'm just copying whatever I have written here, -1 squared. I probably did some -1 factoring here, times alpha plus beta, -1 alpha plus omega 2 beta plus alpha plus beta times omega 2 alpha plus omega 1 beta plus omega 1 alpha plus omega 2 beta. I'm sounding like a drone now, or a Dalek. Omega 2 alpha plus omega 1 beta. Close that thing here. Just so that I could. All this equals to minus 3p. And then somehow, if we're expecting that, you have a -1 squared and you have a minus 3p. This is disastrous. Omega 1 alpha. Yeah, so omega 1 alpha squared plus omega 2 alpha beta. Yep, feel free to skip to if I. Oh my god. If I get the time to go and put timestamps on this, feel free to go to where the end of this calculation horror is. Plus omega 1 alpha beta, and once again, in particular, the stuff that's going to save us at the end of the day is those parts of the complex roots of unity that we proved in part A. Now it equals to minus 3p. That is nasty. You can even do it in one line. Okay. And then stuff starts to cancel. Yep, I'm gonna have to delete stuff here at this point. Okay, hope we got a good view of this. I'm gonna erase it now. Yeah, I'm just going to do... I think it's just a factoring trick here. I wrote the first line, the second line, okay, the third line. So then that is omega 1 alpha squared plus, okay, this is just factoring. This line here is just factoring, clever factoring. Plus 2 alpha beta omega 1 plus omega 2 plus omega 2 alpha squared plus omega 1 beta squared. Did I miswrite? No, that was good. Plus omega 2 beta squared plus alpha squared minus alpha beta plus beta squared equals minus 3p. But omega 1 plus omega 2 is simply just minus 1, so then this becomes omega 1 alpha squared minus 2 alpha b plus omega 2 alpha squared plus omega 1 beta squared plus omega 2. Wait. Can't I also like factor out a... Okay, I'm working too long. Just write exactly as I have. Omega squared. I knew it. Oh, okay, I knew it. I was missing some stuff over from there. Okay, yeah, I should have not done copy all that stuff. Okay. Pain. Okay, so repeat the whole thing again. Very sorry about that. But if you're doing any trickery here, it's mostly just factoring for the most part. Omega 2 plus omega 1 plus omega 2 beta squared plus omega 1 omega 2 alpha squared plus alpha beta omega 1 plus omega 2 plus omega 1 beta squared plus omega 1 omega 2 alpha squared. And I'm reading the wrong line again. Alpha beta omega 1 beta squared plus omega 1 omega 2 alpha squared plus alpha beta omega 1 squared plus omega 2 squared plus omega 1 omega 2 beta squared minus 3p. And now let's do this in color coding here, otherwise I'm going to lose my mind or make a mistake again. This is negative 1. This is also negative 1. Yeah, this is negative 1. This is negative 1. This is omega 1, omega 2, that's just 1. That's just 1. And then that's just 1. Just playing with signs. Eventually, if you go further down algebra, you realize that changing signs is just a fancier way of doing permutations. Dear God. Yeah, that equals minus 3p. Then from there... Okay, good. I could skip a whole bunch of steps here, because like that was just like me doing a bunch of canceling this. So I'm going to skip a bunch of lines. And then we're going to get this all in one go. So we're going to get... Sorry, brain processing. Okay, I think this is good. So then we have omega 1 alpha squared minus 2 alpha beta plus omega 2 alpha squared plus omega 1 beta squared plus omega 2 beta squared plus alpha squared minus alpha beta plus beta squared equals minus 3p. More factoring, factoring again. There's an alpha squared term in common, alpha squared factor in common for free terms here, a beta squared term in common for free terms here as well. So we get, and then the minus 2 alpha beta gets simplified with another minus alpha beta, so you get minus 3 alpha beta plus omega 1 plus omega 2 plus 1 alpha squared plus omega 2 plus omega 1 plus 1 beta squared equals minus 3p. But remember again, this is minus 1. So this actually just cancels out. Okay, this, we're happy. I saw a video of essentially mathematics professor for Fourier analysis. Actually, that makes it more like applied physics or stuff like basic engineering professor like Stanford University, Brad Osgood, basically went on a mad laughter spree after he said that like, and all this stuff integrates to 0. And looked the most unsettling, like, evil laugh I've ever heard, like, mwah, stuff. So then, yeah, alpha squared plus minus 1 plus 1. Yeah, actually, while I'm doing this, just cross it out. Like, this goes boom, boom. Ah. Yes, that's satisfying. So we just get minus 3 alpha beta equals minus 3p. Bam! Get rid of this. We get p equals alpha beta. All that pain just to get a little drop's worth of water. And that's what we want to prove for part 2 of this assignment. Sorry, I didn't write down there. So like, use this to show p equals alpha beta. So I don't know what alpha beta is, unfortunately, but p is basically one part of the special depressed cubic polynomials linear coefficient. Just one factor of it, not the free. Okay. And now I'm using the previous 2 parts, write alpha and beta in terms of p and q. So let me write this down now. So that was, sorry, I forgot to write that down. That was number 2 for part B here. Now I'm going to erase in there, we're going to do like part 3. Okay, just in case I need it. P equals alpha beta. We proved that. Okay. Number 3, using number 1 and number 2, which is already erased, but it's those 2 results here. Those 2 results here. Write alpha beta in terms of p and q. And now to go to that part here. Okay, yeah, we just need to go manipulate those equations now and substitute them in terms of each other. So yeah, we just play with those stuff. So I let p equals, I like beta equals, from this here, I let beta equals p over alpha, and I plug that beta into this thing here, so I get that 2q equals alpha cubed plus p over alpha cubed. Then we keep going with that, so we get, oh, I'm sorry, I did the other way around. I did in terms of alpha, but you can do the other way. I'm just making it consistent with my writing. Alpha equals p beta. So then this is beta cubed, and this is a beta cubed here. And actually the Greeks pronounce it beta. We've been pronouncing all our Greek letters wrong, people. Surprise, surprise. So then cube goes to there and goes to there, so I can multiply a beta cubed to both sides. This becomes a 2 cubed, beta cubed. You get a beta cube here, beta cubed times beta cubed. You add the three exponents together, you get a beta 6. And that's a p cubed. So then if you rearrange this to let one side of the expression equal 0, which we always want because null product property of multiplication is always nice. Beta to the 6 minus 2 cubed beta cubed plus p cubed. Oh gosh, and here's where it gets nasty. Yeah, we can get an identical copy for alpha as well, so this is also valid. This or this. Okay, and now, guess what do we do here? It's even more pain, because what would we possibly do that would give us like nested radicals, which is what we would get. It's a quadratic formula. So we make a substitution. Let u equals beta cubed and v equals alpha cubed. If we put this into there, I guess I just work with this representation here, you get that this whole thing, in terms of alpha or beta, it doesn't matter. Alpha or beta doesn't matter. Transforms into 0 equals u squared minus 2q. Ooh, my u's look like v's here. 2qu plus p cubed. That's your quadratic. It's not a function, but it's like a quadratic parametric curve for u, a relation. And I guess you treat q as a constant and stuff. Then you go and just finally do quadratic formula for that. U equals v, just due to identicalness of that, equals minus 2q plus or minus square root of minus 2q squared minus 4 times 1 p cubed. And I'll be honest with you, especially when I was typing this up for myself, I think it took me a total of 5 hours. And like 3 of those hours I did straight, and the other 2 hours was during another period of time. Again, emphasizing that this is a revision village problem. This is not a good problem that you would expect to see on the actual IB paper 3. Because this is still one question. This is still one question at the end of the day. Divide by 2, so then that gives you 2q plus or minus 4q squared minus 4p cubed over 2 equals q plus or minus, and it's like good evidence. You could like check like the timestamp even further to see if it's like good or not. But then, oh okay, this one was a bit quick. This was a bit quick. Let me go and break this one down a bit. So you have 2q plus or minus 4, square root of 4. We can pull out the square root of 4 from there, which is just going to be 2 at the end of the day. So this becomes 2 square root of q squared minus p cubed over 2. Now this just cancels. And this gives us here q plus or minus square roots of q squared minus p cubed. Yep. But remember that this was just p. This was just u or v at the end of the day. This is so u equals q plus or minus square root of q squared minus p cubed. But u is beta cubed. Plus or minus q squared minus p cubed. So now I do the cube root of this garbage. Beta equals cube root of q plus or minus square root of q squared minus p cubed. Ugly, but that's how it works in the that's how it works in the cubic business. And equals alpha as well. There's a little bit of, admittedly, once you work it through, like a bit of a nice symmetry, which I'll describe in a bit. But yeah, you get those things. And then okay. Yeah, basically show that, like, yeah, that's basically your answer, because, like, actually we have two answers here, because it's a plus or minus, right? One plus will belong to one root, and the alpha will, and the minus will belong to the other root. So then in total, in the end, just through this big giant substitution, we end up concluding that alpha equals remember, because, like, you can only assign the plus or minus to one root. One root will be alpha equals cube root of q plus square root of q squared minus p cubed, and then the beta will be cube root of q minus square root of q squared minus p cubed. And let me color code that here for benefit of the audience as well. Really? There. So we did it, and we survived part B. And that is essentially, believe it or not, what we just did was, no, not yet. It's at the next part, but it'll be Cardano's formula. But this was already a bunch of pain for me and probably for you to follow as well. So now, as Michael Penn would say, this is a good place to stop for now.